Okay. Today we'll have a brief discussion on distributed file system. Now, so far about the file system that we have discussed, there our basic assumption was that all the files are stored on the single machine and the user of the application program runs on the same machine. Now, what will be the scenario if the files are distributed over a number of workstations which are connected over say LAN? Okay. So our situation is something like this. We have a backbone network or say local area network on which we have a number of machines connected. So the situation is something like this. A few of the machines which are connected over the network, they are powerful machines in the sense that they have large amount of disk space as well as memory, and maybe the speed of operation of those machines are also higher than the other machines on the system. So you can have one or more such machines on this network which will be called as file servers. I mean, they are the machines which mainly contain the different files which are to be shared by a number of users. And we don't put any restriction on the locations where a user should work. Okay. So on this network, we'll have a number of machines. Few of the machines will be powerful machines. We call them as file servers. And the other machines which are not that powerful, which will be called as clients. So the idea is something like this: a process which is running or an application program which is executed on a less powerful machine, whenever they require some file, access to some file, it puts a request to the file server. And it will be the responsibility of the file server to deliver the files or to provide access to those files which are requested by the client processes. Okay. So whenever we go for such a kind of model, the file access can be done in one of the two ways. That is, whenever a client puts a request for a particular file, the responsibility of the file server which contains that file, as we have said that we can have a single file server on the network, or we can have multiple number of file servers on the network. So the server which contains that file, it will transfer the entire file to the client who has requested for it. So we can have a model something like this. We have a client process and we have a file server. So whenever the client process puts a request for a particular file, this file which is existing in the file server will be transferred to the client. And because in this case the entire file is transferred to the client, so the client must have some capability to store this entire file. Okay. So the file may be stored either in a small amount of hard disk which is there in the client process, or it may also be cached in the main memory of the client. So this is the client process and this is the file server. Now when the client process completes its use, finishes its use on the file, the client process will write back the file onto the file server. Okay. So this is the modified file or new file which is written back onto the file server by the client, and this is the old file which is requested by the client from the file server. So this is one kind of model that can be used for this distributed file system. The other kind of model that can be used is what is called a remote access or remote file access. There again, we'll have a client process, and generally it is running on a machine which is other than the file server. So we'll have a client process here, and we have a file server which is one of the file servers in the network. The file will reside on the file server. Unlike in the previous case, which is called an uploading or downloading operation. So when the client is getting the file from the file server, we can call it download. When the client is writing back the file onto the file server, we can call that as upload operation. Now in this case, the entire file is not downloaded to the client, but rather the file resides on the file server itself. So this is the file server. Now all the operations that is needed by the client to be performed on these files, on the file residing on the file server, the entire facility has to be provided by the file server itself. So these are the requests and the replies which are obtained by the client from the file server. So you find the basic difference between these two is, in the previous case, the file server is only concerned about downloading the file to the client. Then getting access to different parts of the file is the responsibility of client itself. The file server does not bother about that. Whereas in the later case, the client puts a request for a part of the file, and the responsibility of the file server is to extract that part of the file or that block of the file and only transfer that block to the client. Okay. So all the file access mechanism has to be done by the file server in the later case, or the file access operations will be done by the client in the former case. So this is the basic difference between these two types of operations. The advantage in the later case is that now the client don't have to cache the entire file, so the memory requirement or the storage requirement for the client is much less. Whereas in the previous case, where the client gets the entire file from the file server, puts it into the cache may be either on the hard disk of the client or maybe within the main memory of the client. So the client needs a good amount of memory for caching the entire file. Okay. So this is the kind of operation or the kind of model that can be used if the file size is not very big. Okay. Whereas if the file size is very big, in that case, this is the model that should be used, not this one. Now, whatever the model, whether this is upload download model or caching model or remote access model, whichever model is used, in either of the cases, what is most important is the directory structure, because as we have seen, even in case of a single process system, when the file is not distributed, that what the client or an application program gives is just the file name or a path name leading to the file which is needed. Okay. Then following the hierarchical directory structure or tree structure of the directory, we have to get what is called an inode of the file. So once the inode is available to the client process or the application process, then only the file can be accessed either for reading purpose or for writing purpose or whatever the client process wants to do. Okay. Similarly, in this case, whether we go for this upload download model or we go for remote access model, our basic concern is we have to get the file, we have to access the file residing on one of the file servers. Okay. So here again, the client process should not be bothered about what is the location of the file, which is called location transparency. Okay. So the client need not bother about whether the file is stored on server 1 or server 2 or server 3 or so on, or the server 1 is located in Kharagpur or server 2 is located at Calcutta, all these things. So these informations should be transparent to the client. Ideally, that is what we should have, but implementing that in practice is very difficult. Okay, but what is very important is the file directory structure, or usually the hierarchical directory structure that we usually use. Now, one major part in case of distributed file system is the directory structure can be kept on the same machine, or parts of the directories can be distributed over several machines. Okay, so in this case we have two different concepts. One is called directory service, and then comes the file service. The directory service is concerned about getting something like an inode or equivalent to inode to the application program. So following that inode, it has to access the file on a particular machine, and then whatever is to be done, that is done by the file service or the file server. Okay. So you can have a directory structure something like this. So I can have a root directory called A. Under this, I can have two subdirectories. One subdirectory I can name as B, other subdirectory I can name as C. Under B, I can have a subdirectory, say D. Here I can have another subdirectory, say E, and so on. Okay. Under each of them, I can have a number of directories or files. And I can have a situation like this. Suppose this is the portion which is stored on machine 1, and this is the part of the directory which is stored on machine 2. Okay. So it is not necessary in case of a distributed file system that the entire tree structure of the directory should be contained on the same machine. Even the directories can be partitioned, and different parts of the directory can reside on different machines. Okay. So in such cases, getting access to the file or getting the file inode is very, very complicated. The other important point is whether all the clients which are on the network, they should have the same view of the directory structure, or they should have different views of the directory structure. So a situation something like this. Suppose on server 1, I have a directory structure something like this. A, B, C. Then under B, I can have a number of files or directories. Under C also, I can have a number of files or directories. Okay. So this is the directory structure on a particular file server. The directory structure on another file server can be something like this. D, E, F, and again under E, I can have a number of files or directories. Under F again, I can have a number of files or directories. Okay. So this is the directory structure on say server 1, and this is the directory structure on server 2. And suppose we have got two clients, client 1 and client 2. It may so happen that for both the clients, client 1 and client 2, because client 1 or client 2, they may need files from any of the servers. Okay. So I have to have a global view of the file structures, of the directory structures which are residing on different machines. Okay. So to the clients, a common directory structure can be something like this. So I'll have a root directory. Under root directory, I'll have different subdirectories. Now these subdirectories correspond to, or subtrees correspond to, the directory structure on different servers. So here the situation can be something like this: A, B, C, and the remaining things are as it is. Here it will be D, E, F. Okay. So in this case, both the clients, client 1 and client 2, will have the same view of the directory structure. Okay. Now the other thing is also possible. Our directory structure can be something like this. Here I'll have a root directory. Under root directory, I have A, B, C, D, E, F. So other things remain as it is. Something like this. So maybe that client 1 views this kind of directory structure, whereas client 2 views this kind of directory structure. Okay. So now you find that the directory structure view for different clients are different. So if this is the situation, in that case, if we look for a path name, say D, E, under E, say some file X. Okay. So this is a path name which is valid for this directory structure, because D comes under root. Under that we have E, and under E we are interested in either a directory or a subdirectory or a file named as X. So this is a path name which is valid for this directory structure, but this path name is not valid for this directory structure, because in this case under root I don't have any directory called D. D is a subdirectory of C. Okay. So what is expected is, what is desirable in case of distributed file system is a view like this, that is all the clients who are working on the same distributed file system should have the same view of the directory structure. Okay. Now the next thing is, whenever an application program or a client process runs, most of the cases the file is file which is desired, that is given in the form of path name. Okay. Now the responsibility will be to get something like an inode, as we have done in case of a single processor file system, which identifies a particular file on the file system. Similarly, in this case also we have to get something like an inode to access a particular file of interest. But in this case, because the files can reside on different machines, only inode number is not sufficient. So now every directory should contain a machine number along with the inode number. So for every file or every directory that is to be searched, against every file or every directory, I have to have a binary equivalent, which in case of a single file system was an inode. In case of distributed file system, it has to be machine identification number along with the inode. So I have to have the machine identification number or the server identification number along with the inode number on that particular server. Okay. Because I have to know that which server contains the file, the requested file, and what is the inode number of that file. So here I need the machine number along with the inode number, not only inode number as we have seen in case of a single process system. Okay. So every directory entry in this case has to contain the file name or the directory name followed by a binary number, which is a combination of the server identification, that is on which server that file or that directory is located, and the inode number of the file or the directory on that particular server. Okay. So these two taken together, the server identification number and the inode number, identifies a particular file or a particular directory in the distributed file system. Okay. Now next comes that what will be the operations performed for getting such a number, such an identification number for a requested file or for a requested directory. So let us take a situation like this. Suppose I have a client and the client puts a request for a path name, say A, B, C. Okay. So what you have to do is, whenever such a path name is specified, we have to look up the directory structure to get the inode number, and in this case the machine number and inode number for this component C. C may be either a file or a directory. Okay. So suppose with this the request goes to a server, and the server may contain the entire directory or part of the directory. Okay. So this is the client process which puts a request for this. So we have to look up for this path name ABC. Now if you are fortunate enough that the entire part of the directory containing this path name is located in this machine itself, then this machine, this server will provide you the machine identification and the inode identification of this component C. But it may so happen that the part of the directory which is contained on this machine, so let us call it say server 1. It contains an entry A which points to a directory B, and directory B is on some other machine. So maybe directory B is on server 2. Okay. So in such case, what server 1 will do is, server 1 will reply back to the client asking it to search for B, directory B on server 2. Okay. So it is like this. B is a pointer to server 2. Now on getting this request from server 1, what client will do is, client will try to look up for the remaining path name, that is B and /C on server 2. Okay. Now it may so happen that this contains an entry for B which has a subdirectory C, but subdirectory C is on some other machine. So subdirectory C is on server 3, or this entry C is on server 3. So again this will reply back to the client. Following this reply, the client has to look into server 3 for path name C, and once it gets this path name, this component in server C, it will reply back to the client. Server 3 will reply back to the client with the machine identification number and inode number of C. So this basically points to the file of interest, file or directory. Okay. So you find that every time a particular server has to reply back to the client regarding the status of this lookup. On getting that reply, the client has to put a fresh request to another server which is pointed to the first server, and this process goes on, which unnecessarily increases the traffic on the network. Okay. So this can be slightly modified to improve the network traffic, and in that case what will be done is something like this. Client puts a request to look up same A, B, C on server 1. Now server 1 will not reply back to the client, rather it will put the request directly to server 2 for looking up the component B/C. Okay. Then unlike in this case, again server 2 will not reply back to C. The server 2 will simply forward the request to server 3 to look up for the component C. Okay. On getting this component, now the server 3 will give the request or send a reply to the client C. Okay, and this is actually pointing to the file of interest. So find that the operations which are done is same, but only thing is the message transfer mechanism is slightly different. In this case, always the reply has to come back to the client. On getting the reply from a server, the client has to put a fresh request onto the server that has been pointed to the first server. Okay, and in this case, this search request directly goes from one server to another server. It does not come back to the client. So that effectively reduces the network traffic. So this is how the search mechanism has to be continued, and obviously the final result is, the end result is not only the inode number but the machine identification number followed by the inode number. So once you have the machine identification number followed by the inode number of the requested file on that machine, on that particular server, then a request can be put to the server to make that corresponding file or the corresponding directly available to the client. Okay. Then one of the two models can be followed, either upload download model or the remote file access model. Okay. Now again, in distributed file system, the other problem that is very important is, which is not so severe in case of a single process system. That is, if we assume that we are making use of upload download model, that means whenever a client puts a request for a particular file, the entire file will be downloaded to the client and it will be cached into the client processor, client machine. Okay, either in the hard disk or in the memory. Right? Now after that, the client process puts some modification, makes some modification onto that particular file, and the modified file will be written back onto the server only when the entire operation on that file is complete. Okay. So in the meantime, if something like this happens, that the same file from the same server is requested by some other client before the modified file is written back onto the server. So I have client 1 who is modifying on the file, but that updated information is not yet available to the server. In the meantime, the client 2 puts a request for the same file and it also downloads the file to its internal cache, local cache. Okay. So you find the problem that the client 2 who has put a request after client 1 has started modifying on the file is the old file. The client 2 does not get the new file. So maybe whatever data client 2 is getting, that is an obsolete data. Right? So to avoid that problem, what is done is, what is used is what is called a write-through mechanism. Now what is this write-through mechanism? Whenever the client makes any modification on the file, that modification is immediately transmitted to the server, so that server can also perform similar modification on the server copy of the file. Okay. So in the simplest case, what we have assumed is the client gets a copy of the file in its own cache, and whatever modification is done, that is within the client cache only, that does not go to the server. It goes to the server only when at the end of the operation the client writes back the file onto the server. In that case, we face the problem that while say client 1 is modifying on the file, client 2 puts a request for the file. So it gets the old version of the file, not the updated version, because client 2 has not yet written the modified file onto the server. So to avoid that problem, we put what is called write-through mechanism. In case of write-through mechanism, whenever client makes any modification on the file, the modification will be done in the local copy of the file, which is cached within the client process itself. But whenever a modification is done, that modification information is immediately transmitted to the server. So server, on getting that information, can modify the server copy of the file. Okay. So that if any second client puts a request of the file, puts a request for the file, it will get an updated copy, updated till that time. But again, the other problem comes, that is the network delay, because it is never ensured that the moment the modification information is sent to the server will get immediately because of the network delay. However, such things will always be there, and the designer has to bear with it. Now, again, even if we use this write-through mechanism, even then there can be a problem. The problem in the sense that suppose I have two clients, client 1 and client 2. We have said that we are using upload-download model. That means whenever client 1 puts a request for a file from server for some server, say server 1, it gets a copy of the file in its own cache. Client 2 also gets a copy of the file in its own cache. Right? Now, at the end of the process, what if there is any modification in the file, the corresponding client will write back the file onto the server. If there is no modification, then the file will simply be closed, or even after write back, the file will be closed. Okay, but as we have said when we discussed about the buffer cache, that simply closing a file does not mean that the file content will be removed from the buffer. It is retained in the buffer itself until and unless a situation arises that the same buffer is needed to hold some other file content, in which case the buffer has to be overwritten following LRU approach. Okay, so I can have a situation like this, that the client 1 modifies the content of the file and it closes the file. So updated version goes to server. Now before that, client 2 also accessed the same file, but it closed the file before the file was closed by client 1. Okay. So client 1 cache will contain the updated version, server will also contain the updated version, but because client 2 has closed the file before the file was closed by client 1, so the cache in client 2 will contain the old copy of the file. Right? Now, if client 2 wants to open the same file again, then what the file service mechanism will do? It will first try to see whether the same file is contained in its own cache or not. If it is contained in its own cache, then the file will be returned from the cache itself. If the file is not there in the cache, then only it will be requested from the server. But here I have a situation that client 2 buffer, client 2 cache contains the file, but that is an old copy. So even if the server contains the updated version of the file, but client 2 will get an obsolete version of the file because of the caching mechanism. Okay. So what can be done in this case? We should always ensure that whenever a client wants to open a file, wants to access a file, it should always get the up-to-date file, not the obsolete file. So even if the file is contained in the client 2 cache, whenever any client wants to open a particular file, firstly the file service agent which is running in client 2 itself, that will check its own buffer cache if the file exists. If the file exists, then it will put a request to the server asking for what is the recent version number of the same file. Okay, or what is the last timestamp when the file was last modified. On getting this information, it compares that with the cache copy of the same file within the client. If it finds that these two matches, then whatever is contained in the cache of the client is same as whatever is contained in the server. So the file can simply be accessed from the cache itself. It need not be copied, it need not be downloaded from server 1. But if client finds that the timestamp of the server copy is more recent, in that case, the buffer content, the cache content in the client has to be invalidated, and a fresh copy has to be asked from the server. Okay, and these are the problems which are known as cache consistency problem. That is, whether the content of the cache is consistent with the server version of the same file. Now, whenever we go for distributed file system, because we have a number usually more than one servers in the file system, generally the files are replicated on different servers. The reason is reliability. So even if one server fails, we can retrieve the file or the information from some other server on the network. Okay, so that is what is called replication. That is, the same file is copied on multiple servers in the network. Okay, so one of the aim is to have redundancy, so that even if one server fails, I can get the information from some other server, because the same file is copied on multiple number of servers. The other aim is to have more or less uniform distribution load among different servers. Okay, so a particular process, a particular client puts a request for a file, say A. Now A is contained on a number of servers, say S1, S2, S3, and so on. Okay, so what will happen if the client puts a request to S1, and suppose S1 is heavily loaded at that particular instant of time, whereas S3 is less loaded. Okay, so if the access to this file A is given from server S1 only, then the load on server S1 is going to increase further, whereas this server S3 will remain less loaded. Okay, so to distribute the load evenly among all the servers, in this case what can be done is because the same file is also contained on server 3, so instead of giving access to this file A from server S1, the access can be given from server S3. Okay, so that you don't increase the load on server S1, which is already heavily loaded, but rather you redirect this load to server S3. Now, when you go for this replication, there is an associated problem. That is, whenever a file is modified or a file is updated, then that modification has to be made to all the copies of the same file. Okay, so that is again a costly process. So for this updation, in case of replication, what is done is what is called usually done. I mean, there are various ways in which this can be done, but the popular method is what is called a voting mechanism. Now, what is this voting? Let us assume that there are n number of copies of a particular file F. That means the same file F is contained on n number of servers. Okay, you define two quorums. What is called a read quorum, say NR. NR is read quorum, and you define another quorum NW, which is a write quorum. Your condition is NR plus NW is greater than N. Okay. Now, following these quorums, what is done is whenever a file is to be modified or updated by any client, the client puts a request to all the servers which contains the same file F. Okay. Out of that, if at least n W number of machines agrees for this update, then only the updation will be done. And updation will be done on all the machines who has agreed for it. Similarly, for reading operation, whenever a client wants to read a particular file, a shared file, in that case, at least n or r number of servers must agree for that read operation. Okay, and the version number or the timestamp of the file will be requested from all those n number of machines or the number of machines which has agreed for the read operation. So the machines which agrees for the read operation may be more than nr, but at least nr. It cannot be less than that. If it is less than nr, then read operation cannot be performed. Similarly, while writing, the number of machines who agrees for writing must be greater than or equal to nw. If the number of machines, number of servers which agrees for writing operation is less than nw, then that writing operation cannot be performed. Okay. So for reading operation, when at least n odd number of servers agrees for read operation, all those nr machines, nr servers has to first send the version information. Out of those nr version informations, whichever is the latest, that copy of the file will be read because that is the most recent one. The idea is very simple. Let us take an example. Say we have got file servers, 12 servers. So on 12 machines, the file F is loaded. Let us name those machines as say A, B, C, D, E, F, G, H, I, J, K, L. Okay. And let us assume that the nr equal to say 3 and nw equal to 10. So we find that there are 12 servers. So I have 12 copies of the file F. My condition was nr plus nw must be greater than n. So I have taken nr equal to 3 and nw equal to 10. So these two together is 13, which is greater than 12. Okay. So as we have said that whenever I want to update a file or I want to write anything into the file, the write information at least 10 number of machines must agree for write. And once they agree, the file copies on all those 10 machines will be updated together. Okay. So whenever an update or any write operation has to be made on this file F, at least 10 copies will be updated simultaneously. Okay. So following that, suppose these are the files, these are the copies which have been updated. Now following this updation, when I want to perform a read operation, at least nr number of machines must agree for read operation. All these nr number of machines will first send the version information or timestamp information. So since now nr equal to 3 and at least 3 machines should agree for read, you find that there will be at least one machine which is common. Okay. So when you get the version information from these 3 machines A, B and C, or it may be ABE, it may be ABF, it may be ABJ, whatever it is, there will be at least one machine which contains the recent information. And that is why this condition must be fulfilled, that is nr plus nw should be greater than n. If this is not fulfilled, this is not true, then I cannot guarantee that at least one machine under this read quorum will contain the latest version. Right? So when these 3 machines agree for the read operation, all these 3 machines A, B and C will first send the version information or the timestamp. Then the file server on the client will look for which one is the latest. So it finds that C is the latest. Okay. So the file will be accessed from server C, not from the A or B. Right? If more than 3 number of machines agree, then there is no problem. Suppose four machines agree for the read operation. That also fulfills my quorum. All those 4 machines will send the version information. Okay. Say A, B, C, and D. All these 4 machines agree for the read operation. In that case, both C and D contains the updated file or the latest file. So any of them can be selected for read operation. Okay. Now the problem comes if while writing some of the machines are down, so that your quorum is not full. In that case, what will you do? So in such cases, what is done is it is assumed that there are some dummy machines. So the quorum can be fulfilled using those dummy machines. Okay. So on all other machines who has agreed for writing operation, we just write onto them. But whenever these machines which are down, they come up, the first operation which is to be done is to update their file before those machines participate in any other action. Okay. So following a write, if a read request comes, those machines, until and unless they update their own files, they cannot participate in fulfilling the read quorum. Okay. So following this, you find that such a voting mechanism works well when I have replicated files. This increases the reliability, helps in distribution of the server loads. Okay. And your read and write operations are quite efficient. So these are some few introduction to the distributed file system, how the distributed file system can be maintained, and what are their advantages. Okay. So this stop today.